Hello everyone, thank you for watching my educational video, and the title of this video is about LLC Resonant Converter Analysis Method, Frequency Domain and Time Domain. And here are some brief introductions about myself. I received my bachelor degree from Yanshan University and master degree from Chongqing University, both in China. And I received another master degree from University of Wisconsin-Milwaukee, United States. And as visiting scholar, I was working on a collaborative project at Chair of Power Electronics, Kiel University in Germany. And I received my PhD degree from the University of Arkansas this May. And currently, I'm working as a postdoc at the University of Arkansas, and my research interests include wideband gap devices and their applications. The outline of the video is shown here. First, I'm going to talk about the frequency domain analysis for LLC Resonant Converter, and then I will talk about the time domain analysis for LLC Resonant Converter. Based on a specific converter, we're going to make some comparisons between frequency domain and time domain. Finally, we will summarize the video and also point out the key takeaways. First, let's talk about the frequency domain analysis. LLC Resonant Converter is one of the most popular isolated DC to DC converters, and it has the following advantages: wide soft switching operation range, simple control strategy, and wide voltage gain range. It has been widely adopted in many different industrial applications, including like solar and fuel cell system, EV onboard battery charger, and data center power supplies. So the bottom left shows the structure of a 4-bridge LLC resonant converter, which consists of a 4-bridge inverter, an LLC resonant tank, and a 4-bridge rectifier. And the right pictures show some typical industrial applications for LLC resonant converter. Frequency domain analysis is the easiest way to analyze an LLC resonant converter, and it assumes that the switching frequency equals to resonant frequency. And here we summarize the modeling process for the primary inverter. And as you can see that the output voltage waveform is showing on the bottom for a 4-bridge inverter, which is a square wave waveform. If we do the fast Fourier transform for the square wave voltage waveform, we can see that the fundamental harmonic is actually dominating the square wave voltage waveform. So for the frequency domain analysis, we're gonna use the fundamental harmonics to represent the square wave voltage waveform. So finally, the 4-bridge inverter can be modeled as an AC voltage source, which has the expression showing on here. This slide summarizes the modeling process for the secondary rectifier. Since the converter is always operating at resonant frequency, so there will be no voltage drop across this LC resonant tank. The voltage across the transformer will be the same as the 4-bridge inverter output, which is a square wave voltage waveform. And we can use its fundamental harmonic to represent this square wave voltage waveform. Also, since the converter is always operating at resonant frequency, so the primary side current is sinusoidal, and also the secondary side current is also sinusoidal, as shown on the right side. So both the secondary side current and voltage are sinusoidal, and they are in phase, so that we can model the secondary rectifier as an AC resistance, which has the expression shown here. Finally, the LLC resonant converter equivalent circuit model by using frequency domain analysis can be derived as shown here. The primary inverter is modeled as an AC voltage source, and the secondary rectifier is modeled as an AC resistance, and in the middle is the LLC resonant tank. So here are some definitions for LLC resonant converter. The first one is resonant frequency, which is determined by the resonant inductor and the resonant capacitor. Normalized switching frequency, which is the ratio between the switching frequency and the resonant frequency. Inductor ratio, which is the ratio between the magnetizing inductance and the resonant inductance. Quality factor, which is affected by the output power and also the resonant tank parameters. So how can we derive the voltage gain for an LLC resonant converter? So if we look at the equivalent circuit model, the output voltage is actually across this resistor. So based on the KVL, we can actually list this equation based on the impedance of this branch and also the voltage divider law. And finally, we can actually get the voltage gain information of the LLC resonant converter as shown on the right side. Once we get the equation for the LLC voltage gain, we can actually plot its performance under different load conditions. The operation for LLC resonant converter is actually divided into 3 regions by 2 important curves. The first one is the blue curve, which represents that the normalized switching frequency equals to 1, which is also means the resonant frequency equals to the resonant frequency. And another line is this red line, which is the peak gain operating point for each load. So on the right side, the converter is actually operating in the inductive region, and on the left side is operating in the capacitive region. So to summarize, the LLC resonant converter has 3 operation regions. The first region is when the switching frequency is greater than resonant frequency. And the second region is when the switching frequency is lower than resonant frequency, and also it is at the right side of the peak gain point. And the region 3 is when the switching frequency is lower than resonant frequency, and also it is on the left side of the peak gain. And there's a special operating point, which means like the resonant frequency equals to the resonant frequency. So region 3 is actually not feasible in the real application, as we're showing on the bottom figure, which is a typical operation waveform for the converter operating in region 3. So the converter is actually operating in capacitive region, so the soft switching operation for the primary MOSFET is lost, which is very lossy, and also it generates high circulating current, and it has control stability issue. If we look at the left side and the right side, the converter actually has different voltage gain performance. So in real applications, we really would like to avoid region 3 operation, and we need to consider this when we're designing an LLC resonant converter. This slide summarizes 3 typical operation waveforms for an LLC resonant converter. The left side shows the below resonant frequency operation. The DVS operation for primary switch can be achieved since the inductor current is lagging the resonant tank input voltage, which means the converter is operating in inductive region, and the DCS operation for the secondary rectifier can be achieved because it is operating in discontinuous conduction mode, but it has large circulating current because of this discontinuous conduction operation. And in the middle, it shows the operation at the resonant frequency. It can achieve DVS operation, DCS operation, and also it has low circulating current. On the right side, it shows the operation waveform at above resonant frequency. The DVS operation for primary MOSFET can be achieved. However, the secondary rectifier current is operating in continuous conduction mode, so it lost the DVS-DCS operation, and also it has large turn-off current. So the best operating point for an LLC resonant converter is actually around the resonant frequency. Now, let's talk about the time domain analysis for an LLC resonant converter. Why do we want to talk about the time domain analysis? Well, if you look at the real operation waveform of an LLC resonant converter, you will see the reason. The outside shows the typical operation waveforms of an LLC resonant converter, but for frequency domain analysis, we all assume the converter is actually operating at resonant frequency. And in real applications, if we look at the waveforms, we can find out the resonant inductor current and also the transformer voltage all has significant harmonics. So it will cause a lot of errors if we only consider the fundamental harmonic. For time domain analysis, the assumptions are ideal component and no dead time. So there are 3 operation stages: P stage, N stage, and O stage for an LLC resonant converter. And based on the sequence of this operation stage, we have different operation modes for an LLC resonant converter. And first, let's look at the operation stage. So the bottom figure shows the operation stage of P stage, which means when S1 is on, the the equivalent circuit is actually showing on the right side. If we look at the voltage across the magnetizing inductor, we can see that it is clamped by the positive output voltage, and we call it P stage. And based on this equivalent circuit, we can derive the equations for this operation stage. Similarly, for all operation stage, the equivalent circuit is shown here. If we look at the voltage across the magnetizing inductor, we can see that it is not clamped by the output voltage, so we call it O stage, and here is the model for this operation stage. And for the N stage, we can see that the voltage across the magnetizing inductor is actually clamped by the negative output voltage, and here is the equation for this operation stage. As we discussed before, the operation mode is determined by the sequence of operation stages in half-switching circle, and here are 6 common operation modes for an LLC resonant converter. This table actually summarizes the common operation modes for LLC resonant converter and the different switching frequency condition and different load conditions. Now let's look at how we can derive the model for an LLC resonant converter. Let's take the PO operation mode for example, and there are several characteristics that we're going to use. The first one is symmetric characteristics of current and voltage, and the continuity characteristic of current and voltage. And last one is the energy conservation law. So if we look at these equations, the first equation tells us that initially the inductor current equals to the magnetizing inductor current. And the second equation tells us at angle alpha, the inductor current equals to the magnetizing inductor current. And the third equation tells us that the resonant capacitor voltage is symmetric at the initial point and the end of half-switching cycle. And the fourth equation tells us that the resonant inductor current is symmetric at the initial and at end of the half-switching cycle. And the last equation tells us about the energy conservation law. After we get all equations for different operation modes, the next question is about the mode boundary. Well, the idea is to use assumption and verification. So if you look at the right side, if the normalized switching frequency is less than 1, which means the converter is operating in below resonant frequency, and we assume the converter is operating in PN mode first. And we can use the equation to solve the converter, and we can get the results. And next step is to verify with a small step. We can confirm if the converter is really operating in PN operation mode or not. If not, we can assume another different operation mode, and finally we can get the accurate operation mode for the converter. After we get the mode equations and also the operation mode boundaries, by giving any circuit parameters, we can actually solve the converter. And here we have developed a simulation tool based on the MATLAB graphical user interface. And as you can see that the users can put the converter parameters, and by clicking the calculate, the converter can be solved. Now let's make comparisons between frequency domain analyzed and time domain analyzed. Here, we make comparisons between frequency domain analyzed and time domain analyzed based on this experimental prototype, and the results are summarized on the right figure. The right curve represents for the experimental results, the blue curve represents for the time domain analyzed results, and the pink curve represents for the frequency domain analyzed results. We can see that the time domain analyzed results is actually more close to the experimental results. The difference between the time domain analyzed results and experimental results are the voltage drops across the parasitics. And also, with the decrease of switching frequency, the output power is increasing, so the voltage drops across the parasitics are increasing. That leads to more difference between the time domain analyzed results and experimental results. However, the trend between the time domain analyzed and the frequency domain analyzed are agree with each other. However, on the other hand, the frequency domain analysis shows totally different trend. As you can see that when the switching frequency is below 80 kHz, the output voltage starts decreasing. Well, for the time domain analysis and experimental results, they are still increasing. So imagine that if we are using the frequency domain analysis to design the LLC resonant converter, if our desired output voltage is 65 volts, if we use frequency domain analysis, we will find out that we cannot meet the requirement because the maximum output voltage is only 60 volts. What we can do? Well, we have to decrease our magnetizing inductance in order to get higher output voltage. And in that case, we will increase our circulating current and degrade the converter performance. So the time domain analysis will be beneficial to achieve optimal design for the LLC resonant converter. Finally, I would like to summarize and point out the key takeaways. In today's video, we talk about frequency domain analysis and time domain analysis for LLC resonant converter, and we make comparisons between these two analysis methods. The key takeaways are frequency domain analysis is suitable when the LLC resonant converter is operating around the resonant frequency so that the higher order harmonics can be ignored. The time domain analysis is accurate over the whole operation range so that it is beneficial to achieve optimal design of LLC resonant converter, and the simulation tools are available for the audience. Here is the reference list for today's video, and the simulation tools can be downloaded from reference 3. Thank you very much for watching. If you have any questions, please feel free to contact me.